Jin, of course, is a very well-known CH functionalization chemist from the Scripps Research Institute and a leading member of our center. And the title of his talk is Towards Practical CH Activation Reactions, Substrate, Metal, and Ligands. All yours, Jin, and we can hear you loud and clear.
Can you hear me? Great, yeah. So first of all, thank you, Hugh, for inviting me. And also I wanted particularly to actually really thank all the other speakers. I haven't learned a lot today. It was a wonderful talk. It's just scary to have to give a lecture after that 3 performances, but I will do my best. So as you can see, the title is a little bit sporadic, but I will, because I'm supposed to cover all the collaborative efforts I'm involved in the center, but I will also touch a few more general subjects that is broadly relevant to CH elevation. And as you can see, the outline, I will really explain how do we develop a sustainable catalytic cycle. Some are really new, some are older ones, but we're trying to expand and improve them. And then focus on also the message of developing new metal catalysts, because particularly the cheaper metals. And then finally, of course, the center of our program certainly is to develop new ligands to really improve the selectivity. And what I have to apologize is what I will not be able to talk about is a larger proportion of my involvement in the center is I actually am responsible or coordinator for the total synthesis group, subgroup in the center. And as you can see, the long list of the leading expert in synthesis, we have been working extensively on using CHF-VS, specifically multiple step CHF-VS for total synthesis, and we're making a lot of progress, but I will not talk about that due to the time limit. Next slide, please. So the first slide I really want to discuss is actually selectivity. After all, the title of our center is called Selective CH Functionalization. And indeed, we hear this challenging question all the time. That is when and how you're going to selectively functionalize CH activation, CH bond. And that, of course, it's one of the most inspirational questions. But if you really think about it deeply, and actually it's not necessarily all that meaningful to synthetic chemists, because you really have to ask, what does that mean? What kind of selectivity you're asking me to achieve? That is a very important question practically. And why I'm saying that is because if you think about a double bond chemistry, of course, when people tell you to achieve selectivity, you know what they are asking for. And quite often you are referring to Markovnikov or anti-Markovnikov. That's most of the cases. And in the less common scenario, probably you're talking about 3 double bond in the substrate, and you're really concerned with how to differentiate the tri-substituted double bond from di-substituted double bond or even tetra-substituted double bond. So really, you know what the question is about, and you know how to solve that problem, at least to making an effort towards that. But in CH elevation, it's quite a different story, because almost in every case, in each case, your substrate will have multiple CH bonds, and they are really, really similar in many cases. Although you could argue from John's beautiful talk, in many cases, you could divide them between tertiary CH bond and secondary CH bond. That is beautiful, of course. And indeed, our center has huge effort on that direction, try to distinguish tertiary CH bond and secondary CH bond. But if you're a synthetic chemist, you will realize very quickly that doesn't really solve the problem altogether, because in many cases, again, in synthetic application, you will be challenged with substrate that have many, many secondary CH bond or tertiary CH bond. Then what are you going to do? Basically, if you make an analogy to that, I would say it's very similar to walking in the desert without a compass. You really don't have anything that to recognize. So it's very important. You have to really think about deeply what selectivity you want to achieve, and you try to look for something that you can recognize. And that is what we are really heavily thinking about in the center. And we decided really to focus using the distance and geometry as a compass. And as you can see from those molecules, if you look at the red CH bond, the distance are different. And if you look at the blue CH bond, the geometry are different. And yet, you can use the same catalyst, use the same kind of reagent. You can recognize the distance and geometry and achieve predictable selectivity, right? And then that's the key message I want to talk about. And as you see from the bottom, that's a center collaboration with Mowasaki. We were able to show in very complex setting, we can function as a CH bond in a remote position. And of course, it's still far away from being ideal and broadly useful. We still are trying to improve the scope. Next slide, please. And And I think the same message could be also repeated again with sp3 CH-activation. On the first equation, you see the 9 CH bond, and each can have different distance in relation to the function group. And that's what I meant to emphasize, is you really have to refer to existing function group. Otherwise, you just don't have a referencing point, like I said, in walking in the desert without a compass. So it's very important to utilize the existing function group if you're a synthetic chemist. Unless you're a petroleum chemist, then of course that's a different story. You can just worry about hexane, butane. Then you're worried about only primary, maybe secondary CH bond. But for synthetic chemists, you really have to think about what function group you are interested in, and then try to build a relationship as a referencing point to that function group, and then try to work on distance and geometry to achieve the selectivity. And the second row, you can see that's a very simple subject, but we're trying to work on is how do we achieve the better CH activation, then move on to gamma or maybe delta, or eventually we want to go to the omega even, right? And that is the idea that we have taken. And I think that would fit into the scheme of the holy grail goal of the center, that is to achieve selectivity. And there are certainly many approaches to it, and that's our approach, how to achieve the selectivity. And once you have that, then of course immediately what you want to do, next slide please. Once you know where the CH bond you want to functionalize, then of course you want to have a huge amount of choices, so you can introduce diversity or complexity. And if you look at this list, and through the last 12 years effort, now 14 years effort, I think that this list become fairly respectable. This is what we can do. But of course, the problem now is how to do this more efficiently. I think we have a good level of diversity, but what we really needed to do now is to improve the efficiency, so we can go multiple ton scale, can do process chemistry. Next slide, please. And to do that, clearly the foundation is to invent or develop new catalysis. And if you look at this slide, it has 4 completely different catalysis catalytic cycle, and each of them have their own advantage and disadvantage, and they are all orthogonal and complementary, right? If I may go through very quickly. The first catalytic cycle is palladium 2,4. It's very beautiful in terms of making the bond. It's very powerful, but the disadvantages at the moment, the oxidant is too expensive, and also the selectivity is quite often an issue in forming the bonds. Quite often you get a mixture. And the second catalytic cycle is palladium 2,0. The big advantage, of course, is 2,0 is very simple. You can use oxygen as a turnover oxidant, but on the other hand, the transformation we still have to expand. Although we kind of really initiated this catalysis for cross-coupling, but at the moment we are not doing, we would like to expand this to many, many more transformations. So that's a disadvantage. And the third one is a very unique catalysis, and that's what I'm going to focus on today, is a palladium 0, palladium 2 catalysis. And why we chose to work on this in the center, because the center has a very important agenda, is to achieve sustainable catalysis. And this catalysis is very well suited for that purpose, because if you look at the catalytic cycle, it's actually almost identical to the Heck cross-coupling. That means you don't need to use external oxidant. It is self-sufficient to close the catalytic cycle. But the big problem is the transformation scope of the scope of the transformation is miserable, especially for sp3 CH activation. Basically, intermolecular version does not exist until very recently. The center was able, through our effort in the center, we were able to demonstrate this is indeed now possible, and we're trying to expand that as well. And of course, the transformation is still very limited, but today I will show you we have been able to expand to 3 different transformations. And finally, what is emerging from the center, from our lab, is to also develop another catalysis. We call it redox neutral catalysis. As you can imagine, that means you don't need to use any oxidant, right? Because it's redox neutral. The palladium stays palladium 2 all the way through the catalytic cycle. They never change the oxidation state. You start with palladium 2, and then use the electrophile, and then you make the bond. You still stay as a palladium 2. And I'll show you 2 examples. Actually, we have a number of examples coming, but I won't have time to show you today. Next slide, please. And I should definitely mention another extraordinary catalysis is the 5th catalytic cycle that we have been working on in our lab, is this Catanani catalytic cycle. It's one of the most elegant and complex catalytic cycle. But unfortunately, at the moment, for catalysis, for synthetic application, it has many, many limitations. And we are trying to be inspired or borrow some of the steps in this catalytic cycle and develop some very general chemistry. But I won't be able to talk about that today. Next slide, please. So here is a brief history. I can't possibly tell you all the numerous examples that in 1970s, 1980s, how people have used this kind of platinum zero catalysis, like a Heck coupling, to do CHF-VS. But for sp3, it's still very sporadic, very few, only a few examples, right? And the intramolecular one really is some of the leaders are Dyke, and then Bedoin, and Keith Faneuil, the native professor. But if you look at this transformation, it's very obvious. From those transformations, it's not clear how you can do intermolecular transformation. Quite often, as a synthetic chemist, you know some reactions, when you see the intramolecular, you know you can do intermolecular. But in this case, it's not, because the catalytic cycle, the coordination structure of the palladium would have a completely different requirement. For the intramolecular, as I showed you in the middle equation on the left-hand side, the palladium is attached to the substrate by the arrow bromo through covalent bond. And so therefore, you still can afford to have a vacant site for the phosphine ligand to be coordinated. But if you want to translate this catalytic cycle into intermolecular CHF-VS, then if you draw the transition state, you realize there's no place for the phosphine ligand, right? Because you have a directing group from the substrate or functional group from the substrate that has to coordinate. So really, you have to kick out that phosphine ligand. So then the big question is, can that still do CHF-VS? And as you can see, the first example we were able to demonstrate by Masawasa. Now he's an assistant professor in Boston College. As Melanie Sanford mentioned, he invented this very powerful directing group. This AMI can do this platinum zero catalyzed sp3 CHF-VS for the first time. And of course, later on, in collaboration with Jamal within the center, we have been able to establish the transition, very interesting transition state, how this chemistry works. Indeed, the phosphine ligand, although it's still coordinated, but it's very loosely dissociated. So it's kind of, they basically share the coordination with the weakly coordinating directing group. Next slide, please. So from this, breakthrough, we were able to then expand to alkynation chemistry. And that is very interesting. Using the alkyne bromo, we were able to discover a new ligand that can accommodate sp3 alkynylation chemistry. And this reagent has been commercialized now from Aldrich. Next slide, please. And then this is the subject scope. I don't think I should go through all of them, and looks pretty good, and you can tolerate a wide range of substrate. Next slide, please. And the big challenge, of course, you can argue that alkyne bromo can behave similarly to aryl iodide, because you can imagine that happening. But if you want to do analogous sp3 amination, that would be a big challenge, right? As you can imagine. How does that happen? So that becomes a very big challenge within the center to do intermolecular sp3 CHF-VS. And as you can see, the idea is to mimic the aryl iodide by devise a new reagent we call NO reagent, right? NX, to mimic the aryl X. So we hope the palladium zero would insert into the nitrogen-oxygen bond, and then to mimic the aryl oxidative addition of the aryl halides. And then the big challenge is if that species can actually coordinate to the substrate and still cleave the CH bond. That is, of course, unknown, because that has never been shown before. Intermolecularly, can that nitrogen palladium bond still cleave sp3 CH bond? And it's very interesting. Almost at the same time, when our work is done, John Harwick published a very nice work, intramolecular tested strategy using NO bond intramolecularly. They can cleave the sp3 CH bond. But of course, the intermolecular is quite a challenge in a different story. And if you can move to the next slide, please. Next slide, yes. You can see by screening the ligand, well, in this time, we have to design a new ligand with the electron deficient ligand. And that is, of course, hugely inspired by the computational study from Jamal's computational study. We already knew that the phosphine ligand is very loosely associated with the palladium. So therefore, we start to really make a ligand that's electron deficient so that to weaken the coordination to help the CH cleavage step. And that indeed works. Next slide, please. Using this chemistry, we were able to make some very interesting drug molecules, antagonist or agonist. Using this, it's very interesting disconnection to make that CN bond, and otherwise very hard to make. Next slide, please. And this is a brief catalytic cycle. you started with a palladium 0 catalyst, insert into the NX bond, you generate this amido palladium species, which was miraculously able to collaborate, to coordinate with the amide auxiliary, the amide substrate, and then that can still cleave the CH bond and close the catalytic cycle. So you don't really need an external silver or any other oxidant. That's the idea, I guess. And we hope really to expand this chemistry, but at the moment still it's challenging. Next slide, please. And as I said, we are at the same time, we are also interested in other approach to build up sustainable catalysis within the center. And another idea we really have been working on is palladium 2,2. And if you pay attention to our early work, we have always mentioned in our paper, in this alkylation chemistry, it's not palladium 2,4. Although many people always thought we are doing palladium 2,4, it's actually palladium 2,2, because it's very hard to imagine without any strong coordinating substrate or ligand, and using alkyl chloride without silver, it's very hard to imagine you can do a 2,4 chemistry. We really believe what happened here is we made a very simple Grignard reagent disconnection. You basically are doing CHF agent to replace the Grignard reagent, and you can react with alkyl halides. And the beauty is, of course, you don't need to worry about oxidation chemistry. You don't need to turn over using oxidant. So it's very cheap, it can be. And mechanistically, we have also provided a very interesting evidence by performing catalytic deuteration. Actually, that turns out to be practically very useful for drug labeling, deuterated labeling study, for metabolism study. But this is a very novel catalytic deuteration method. And again, that shows you using simple deuterium electrophile, you can react with the air of palladium. Again, that's consistent with the air of palladium as a simple nucleophile, like Grignard reagent. And of course, the iodination reaction fits into this regime as the paradigm as well. And the recent paper just came out with Jamal's collaboration with Jamal, did some very nice, with Brandon and Jamal, the student did a very nice calculation to show indeed the iodine was not oxidized in palladium 2,4. Indeed, the carbon palladium act as a nucleophile, just like a Grignard reagent, and they pretty much did an SN2 reaction. Attack the electrophilic iodine, pick up the iodine, and the catalysis goes again. And that's why this catalysis don't need any silver. They can still turn over very well, 0.5 mole % palladium. I think in principle, this catalysis can go on forever. Should be able to use 0.1 palladium catalyst and then go on to do process chemistry in ton scale in the future after further optimization. And of course, we will have many, many examples coming using this idea to develop catalysis. Next slide, please. And I think, as I promised in the title, I will be very, very brief, that we are also interested in, of course, copper chemistry using a cheap metal. And the first example disclosed in 2006, as you can see, the subject scope is miserable. It's only 2 phenol pyridine. But this has caught a lot of attention, of course. But so far, it's still very challenging. But finally, within the center, we have made some progress, a small step forward. I would say the biggest result has yet to come, but we are on the way to publish some really big breakthrough using ligand to control the copper catalysis chemistry. Next slide, please. At least we have been able to show that copper can catalyze some very interesting amination chemistry. As you can see, they can be very complementary to the palladium catalyzed the CH activation reaction in terms of tolerating wider range of heterocycles, right? You see many heterocycles, nitrogen atoms. Usually it's very challenging, but in this case, we can do all of those coupling partner as well as a substrate on both ends. And we can also do trifluoromethylation using TMS, which is a TMS CF3 reagent, which is hard to do. But using this copper catalyzes cross-coupling reaction, we can put on the trifluoromethyl group on this substrate. So that's very encouraging. Next slide, please. And finally, I want to finish with a key message from the center. The effort is to develop better ligand. And the key, of course, is to understand how ligand works. And we published this ligand in 2008, but really it was within the center. We really now have hugely improved our understanding how this ligand worked to control the stereochemistry, to deliver enantiomer selective CHF agent, to improve the catalytic turnover. And I should really mention a seminal work from computational study from, again, Jamal, Ken Hawk, Professor Wu from China, and also a kinetic study from Dana Blackman and numerous basically collaborations, numerous projects that eventually led us to draw this very simple, most updated transition state I showed you here. Although this may not be final version, but I think that we are very happy with this model because they can pretty much predict almost every cases the absolute stereochemistry that we are producing in anti-selective CHF-VS. And we can also use this as a very good guidance for developing better ligands. And let me just be very brief. What's the consequence, impact of this joint study? So far, the catalysis-wise, we have 3 examples. We can use 0.5 mole% palladium. And that is a very high standard in this field. In palladium catalyzed CHF-VS, that's a very, very high level of catalysis, okay? And there was a couple more you haven't seen yet, but we're submitting very soon. And in terms of broader impact of this ligand, there are so far 50 publications not citing this ligand, but really precisely using this ligand for enabling new CHF-VS reactions. 20 examples of enantioselective selective CHF-VS using this chiral ligand. And 3, actually I should say 5, there are 2 more just came out, I think. 5 total syntheses using this ligand to accomplish total synthesis, and 2 industrial applications. So clearly, a joint effort has led us to, to move on to next level to improve the efficiency of ligand-controlled catalytic CHF-VS reactions. And finally, next slide. The most important slide, of course. I want to highlight again some of the major contributors. I've already mentioned Masawasa, and in the center, Jen, he is the main player. But of course, Marcus Farmer and the new student Tyler just joined the center efforts. And I think I should also mention Xiao Qian was very important on the iodination chemistry within the center, and he's now a professor already in China. And Kiri Ingo did a lot of kinetic study. He's also a professor now in Scripps. A lot of study on the ligand design early stage that has been very important for the center effort. And of course, I should highlight the support from the center grant, because this talk mainly focused on all the project that's carried out within the center. And I should definitely also mention many industry collaborations. That's very, very good for the center for broader impact, and as well as really pushing us to the next level to identify new challenges. And I thank you all for listening.
Okay, Jin, thank you very much. That's a really great talk. Now, while we're waiting for questions to post, I have one question to ask you, and that is, and this is not a serious question, what is the wonderful drawing you have behind you on your wall?
Oh, that was last night. I had a huge debate with Barry Sharpless, and then half of the drawing was Barry Sharpless. He destroyed my chalkboard.
It looks very impressive. I think you should, it could be the new wave in art. Let me tell you.
Believe it or not, we were debating on CHF-VS with Barry Sharpless.
We still haven't had any questions yet. So has anyone got some questions for Jin?
It takes a little while to come through from the YouTube. It's a bit behind.
Well, at least I was dead on time, right?
Yes, it was all the others that were a little bit late. Well, while we're waiting for if there are any questions, I should mention the head count. It's been very disappointing, I'm sorry to say, because I do think we're still undercounted really badly. So far, we've only had 1,295 people joining the symposium, and I'm sure it must be closer to 1,400, but it's a fantastic total. And obviously, we've had 4 really spectacular speakers giving great talks, which is why we've had such an amazing turnout for this symposium. Okay, Jin, I've got a couple of questions. One from India. Would distance really matter for meta CH activation, or for that matter, remote CH activation? Ultimately, the palladium center has to have a square planar geometry in the palladium 2 state, the angle remains the same, basically?
Yeah, that's a very good question. The distance actually doesn't matter hugely, and you can actually so actually from India there was a great work from Maitai, a young assistant professor, and designed some beautiful template using this nitrile template, and you can see there by controlling the distance, a different substrate, you need to tune a little bit of the distance. Sometimes, yeah, it doesn't matter the distance. So you can tune the linkage, and then depending. It's benzoic acid or phenolacetic acid or propionic acid. When the distance gets long, you have to tune the template a little bit to fit.
Okay, a question from Ohio State. In your reactions, what is the most robust generalizable directing group? What is your dream directing group?
Yeah, so far at the moment, as Melanie Sanford mentioned, that amide directing group is extremely robust. But the dream directing group will not be that one. Actually, it's yet to publish. We haven't published yet. So really the best one has yet to come. And I think within 2 years, you will see most of our chemistry will be out of date. I think it will be totally new. The directing will be new. The approach will be new. And I think it really all matters is the ligand. Once the ligand is really powerful, the directing will become less important. I think that probably is the answer to that question.
Great. Okay, I'm not sure where this question is coming from, but is the concept of weak coordination also applicable to other metal catalysis like rhodium-3, ruthenium-2, and iridium-3?
Absolutely, that's a wonderful question. Actually, that has been basically that has been vigorously proven already, and it's yet to come. But I think for those papers they published rhodium, ruthenium, they're using weak coordination chemistry, but probably they didn't necessarily realize how that is helping. But I think there are a number of key papers coming specifically to really demonstrate that weak coordination is so much better for ruthenium, for rhodium chemistry, much faster, even for remote chemistry as well. So the weak coordination is very general, except not quite general for copper yet. But as I said, we have some new chemistry coming with copper. We will be able to use weak coordination as well. But the rhodium and ruthenium certainly dead on, no problem with weak coordination.
Okay, well, Jin, thank you for a spectacular talk.